Welcome everybody. My name is Francesco Battistoni and I'm a postdoc at Université Bourgogne-Franche-Comté. Today I'm going to talk about generalization of a Pohst inequality. This is a joint work with Giuseppe Molteni from University of Milan. Before I start, let me thank Junior Mathematician Research Archive for accepting my contributed talk. The goal of this seminar is to find the maximum value Mn of this multivariate polynomial Qn. Qn is defined this way as a product of these factors, where the variables xi assume values over this cube. They are real numbers between -1 and 1. Here I give you an example of this polynomial, the one in dimension 3, which we write in this triangular form, where every factor multiplies each other, because it will be helpful for later discussions. In particular, it helps in understanding that there is some symmetric behavior in these polynomials. What do we know about these maximum values Mn? Pohst conjectured that the maximum of these polynomials is equal to this value, 2 elevated to the integer part of n+1 over 2. And the maximum is attained at this point, -1, 0, -1, 0, and so on. It is very easy actually to prove that this point gives this value, but it's not that easy to prove that this is indeed the maximum value. Pohst was able to prove this, but just for dimension less or equal than 11. Why are we interested in these polynomials? This has to do with algebraic number theory. We consider a totally real number field K, which has degree at least 2, has no proper subfields, and moreover is generated by a unit, epsilon. Remak was able to prove the following inequality. The logarithm of the discriminant of the field is bounded by the regulator elevated to a power which depends on the degree, times a constant Ln, which is sharp and depends on n, plus a logarithmic part, which contains this product, where the numbers epsilon I are the conjugates of our generator epsilon, which are ordered by increasing absolute value. Now, if you take this change of variables, you get that the numbers xi are between -1 and 1, and most importantly, you have an estimate for the product in the logarithmic part. This is bounded exactly by the maximum of the polynomial Qn-1. In fact, this estimate is nothing but the supremum of the left product taken over the n-poles of real numbers which satisfy the increasing absolute value condition. So in order to solve this number theoretic problem, we need to study the polynomials Qn. How to detect these maximums? How to prove that they are the real maximums? For low dimensions, this is very easy. M1 and M2 are both equal to 2, and you can verify this by using standard partial derivatives procedure. But as the dimension n increases, this local analytic process becomes unfeasible and unsustainable. Instead, we need something different, something more global. And the idea, which was employed already by Pohst, is the following. Given a vector of signs, epsilon, which contains n signs, which are either -1 or 1, we consider the following function, which is now defined over the positive cube, 0, 1 to the n. This function Qn epsilon, you see, is defined very similarly to the configuration, but now the xk are positive, and the sign information is collected in this product here. We call the function Qn epsilon a configuration of Qn. We want to prove that every configuration for each one of the 2 to the n choices of epsilon, the resulting configuration satisfies Pohst's inequality. If every configuration satisfies Pohst's inequality, then also the polynomial Qn satisfies it, and we obtain the desired value for Mn. We give an example of a configuration. take again the polynomial Q3, and this vector of signs, plus, minus, minus. Now remember, the xi are positive, and the sign information is collected here. So you see now this factor is a 1 plus x2. And now the graphical shape of these polynomials will be very helpful for our problem, because our configuration Qn epsilon, together with its sign information, can in fact be represented by a triangular array which is formed by signs plus and minus, where each sign at a place ij corresponds to a product of signs. For example, the very same configuration from before now has this graphical shape associated to it. You see, this diagonal is given by the signs in the vector sign. This minus is the product of this plus and this minus. This plus is the product of these two signs. This last sign is the product of all the signs in the vector of signs. And similarly for this other configuration in dimension 5. From now on, every n times n triangular array C, which is formed by plus and minus, will be called a graphical scheme of dimension n. Please notice that not every graphical scheme is the graphical scheme of a configuration. But what is important is that every graphical scheme is associated to a function over the positive cube defined similarly to the configurations, because now the variables are positive and the sign information is collected here. And so what we are going to do in the rest of this work, instead of studying configurations from an analytical point of view, we look at the associated graphical schemes. As I said before, this was in fact Post's original idea, to associate graphical schemes to configurations. And in more detail, the idea was to recognize patterns inside a graphical scheme. Each pattern corresponded to factors of Fc bounded in a certain way. For example, if you have a graphical scheme and you detect a plus, then the factor corresponding to this plus is less or equal than 1, because it corresponds to a factor less or equal than 1 thanks to this trivial inequality. Similarly, if you detect an horizontal segment or a vertical segment like this on the same row, this on the same column, then the factors corresponding to these patterns are both bounded by 1, thanks to this trivial inequality. We also have more complicated patterns in graphical schemes. For examples, we have squares like this. Every such square is bounded by 1 because of this inequality, which is less trivial. And finally, every such triangle on consecutive rows and consecutive columns is bounded by 2, because these triangles, in the end, are nothing but the polynomial Q2, which we already know is bounded by 2. But so, if you are able to cover your graphical scheme with patterns, then this means that you are able to give a precise upper bound for the associated function fc. We give a notation now, given a positive number m, we say that a scheme is less than m if the associated function fc is less than m. And now we prove the first result. Consider this configuration of Qn epsilon minus, which is given by a vector of signs with all negative signs. Then this configuration satisfies Post's inequality, and the proof relies on the use of graphical schemes. If the dimension is 1 or 2, the claim is trivial. Otherwise, we work by induction, and we assume that the dimension is at least 3, is odd, and that our claim is true for smaller dimensions. We consider this configuration, the one with negative signs. It is represented by this graphical scheme. Such a configuration has alternating signs. We have these two first rows of alternating signs. And then for the remaining part of the configuration is exactly the configuration with negative signs in dimension n-2, which by hypothesis satisfies Post's inequality. So now let us focus on the first two rows. In the first two rows, we recognize, first of all, a triangle in the first two columns. And a triangle, from what we have said before, is bounded by 2. Then we have consecutive squares, starting from this. And each such square is bounded by 1. Finally, we have a vertical segment, which is again bounded by 1. But so this means that the first two rows give a contribution which is at most 2. And so if we put all together, this means that the configuration with negative signs in dimension n is less than 2, which corresponds to the first two rows, times the post upper bound in dimension n minus 2, which gives exactly what we want. So we proved that Pohst inequality is true for this configuration. And the proof is completely similar if you consider n even instead of n odd. But now we need to work also with other configurations, and we need a different idea. The new idea is the following. Instead of just detecting patterns, we want to detect and replace patterns with other patterns. And every time we replace a pattern, it is because it is the result of an estimate. We give again some notation. If we have two graphical schemes, we say that C is less than C prime if the corresponding function fc is less than fc prime. For example, if we're able to detect a plus, a point P, in our scheme, then we can replace P with a minus. And this gives an inequality of graphical schemes, because it corresponds to this trivial inequality. Similarly, if we have an horizontal segment, H, we can replace it with this horizontal segment, with the signs which are now exchanged, because again, this corresponds to this inequality. And the same holds for a vertical segment, V. Exchange the signs to get an inequality of graphical schemes. Finally, we have again an estimate when we take a square and we replace it with a square with the signs which are now exchanged. This corresponds to this estimate, a bit less trivial, and gives again an estimate of graphical schemes. So every time we make a replacement like this, we make a move, we act on our graphical scheme C, and we produce a new scheme C prime, which by result of these moves is greater than C. Please notice that if C is a configuration, the new scheme C prime may not be a configuration. And before giving our result, we need to state this definition. Given a graphical scheme C, we say that the sign Cij is wrong if Cij satisfies this relation. Otherwise, it is correct. This definition is such that the only graphical scheme which has only correct signs is exactly the configuration defined by negative signs. Consider, for example, these two schemes, which in fact are configurations. The label signs are wrong signs. Here we should have a minus, here a plus, here a plus, here a minus, and so on. But now look, for example, at the first scheme. These two wrong signs form a pattern, form an horizontal segment. And to the horizontal segment, we can apply the move H, exchanging the signs and correcting the signs. And the move H gives a new scheme which is greater than before. Similarly, here we can apply a move V, obtain a new and bigger graphical scheme. Similarly here, we can apply a move S and a move V in order to correct these wrong signs, and we obtain a graphical scheme which is bigger than the previous one. But applying these moves, applying these corrections, the scheme that we obtain is in fact the correct scheme. The configuration defined by negative signs. So we wonder, is it true? Is it always possible that every configuration is corrected with these moves? Because if this is true, then this means that every configuration satisfies Pohst inequality. And our result is that this is indeed true. Take any configuration C of Qn, then you can always find a list L of moves P, H, V, and S, which corrects C into the configuration defined by negative signs. So, as a corollary, we get that every configuration satisfies Post's inequality, and this means that the maximum of these polynomials is exactly the conjecture value. How to prove this result? This comes from an algorithmic procedure, which is defined by induction on the dimension of the configuration. If the dimension is equal to 1, then either our scheme is a minus, and so we are done, or it is a plus, and so we apply the move P. This is the first move. Let us assume now that the procedure works up to dimension n-1. We are considering C of dimension n. We take then C prime, configuration of dimension n-1, obtained by removing the last column, the nth column. By inductive hypothesis, we have a list L prime of moves, which applied to C prime gives this estimate in dimension n-1, gives the Post's estimate. What we want to do is to look now at the signs in the nth column and correct the wrong signs by adding new moves, and these new moves may also overlap with all the moves in the list L prime. We are not going to give all the details, but it is important at least to give the fundamental steps of this procedure. As we said, we want to examine the nth column. So we look for wrong signs minus starting from the bottom. If the sign Cij is a minus and is wrong, we have to decide whether to apply a move V or one between H and S. And how to decide this? There is a precise criterion. We need to sum the signs to the left of Cij and the signs below Cij. We get two sums, Hij and Vij, which one can prove are opposite to each other. So only one of them is positive. So assume that Vij is positive. Then what do? We pick the first wrong plus available below Cij, and we add to our list a move V, which corrects our minus and this wrong plus. If instead Hij is positive, we pick the first wrong plus to the left of Cij. Now, if this plus by inductive hypothesis is corrected by a move in L prime, and we can have several moves. But if it is corrected by a move V, we replace the move V with a move S. If instead was corrected by a move P, we replace it with a move H. Finally, once we have done this for every wrong minus on the nth column, there may be some wrong plus on the last column. These wrong plus remaining are corrected then by moves P, which are added to the list. As I said, these are just the fundamental steps of our algorithmic procedures. There are many subtle issues that one needs to check in order to show that this procedure is really well defined. For example, here I say that we pick the first wrong plus available, but one needs to prove that there are wrong plus available every time we are in this situation. There are many details about this, and I invite everybody to look at the preprint in order to check these details. What I want to do now is to apply this algorithm to some specific example, like, for example, this configuration of dimension 6. We want to apply the algorithm to this and correct this in order to satisfy Post's inequality. Remember, we have to work by induction on the columns. So we start by column 1. Column 1, we have no wrong minus. There is only one wrong plus. So we apply a move P, which is added to the list. Column 2, we have this wrong minus, for which H is positive. We need to look to the left. And there was only a move P, a wrong plus corrected by a move P. So we replace V, P, by a move H. Column 3, we have this wrong minus for which V is positive. So we apply a move V to this minus and this plus, which is wrong. And so we add the move v. Similarly, in column 4, we have this wrong minus, for which we apply the move v. Now, instead, in column 5, you see here, for this wrong minus, we have that h is positive. So we need to check this plus. This plus was corrected by a v, so we replace this move v with a move s. You see the previous v is no longer, and now we have this move s. Finally, in column 6, for this wrong minus, we have that v is positive, so we apply this move v. This is a wrong plus, in fact. And we have this wrong minus, for which instead h is positive. And so we have this wrong plus, which was corrected by a v. We replace the v with an s, which corrects these 4 signs. This gives exactly the correction for the configuration. So it gives that the configuration satisfies Post's inequality. And as we told, this holds for every possible configuration in every possible degree. So this means that for every possible degree of a totally real number field with no proper subfields, Remax estimate has now this form. The logarithmic part is now precise, depends on the integer part of the degree over 2. And I want to conclude this exposition by giving further problems, because we are interested always in a number theory context, and we want to do something similar also for number fields which have one complex embedding. So we go from totally real number fields to number fields with one complex embedding. One can verify that there are corresponding functions Qn, which are similar to these ones, but they are now more complicated because, first of all, one needs to specify the ordering of the complex roots when we make the change of variables. And this gives further subcases to examine. But secondly, we also have some square root factors in the new polynomials Qn, which complicate the behavior of these polynomials. Nonetheless, numerical heuristic suggests us that by using again graphical schemes, we could obtain an iterative behavior again of these maximums for the polynomials Qn. In fact, we think that depending on the parity of the degree, the 2 possible maximums are either this one, which is in fact very similar to the ones for the totally real case, or this one, which instead is a bit more complicated. But again, we think that there is this iterative behavior, and most importantly, we think that there could be a way to obtain this by using again this machinery with graphical schemes, which obviously needs to be refined for this case. I want to conclude this exposition by giving you the references for our work, and I want to thank you for listening and watching this video. I hope that you enjoyed it. Thank you very much.